Hello class, today we're on 5.2, the definite integral. So remember the videos from yesterday, or from last lesson. Remember that the integral is the same as the antiderivative. So we're going backwards here when finding the integral from what we're used to. Also, there are two kinds of integrals, definite and indefinite. Today we're going to be talking about the definite integral. The indefinite integral is the general integral. So if I were to give you a general function and you found the integral, that would be the indefinite integral. While the definite integral, while still being a general integral, has bounds. So we have an upper bound and a lower bound. And so we actually solve for stuff when dealing with the definite integral. So this is what an integral looks like. This big S thing is our integral symbol. And we have an upper bound and we have a lower bound. And then we have our function, our integrand, which is the function that we're integrating. And then we have our dx portion. That goes away. This is the thickness portion that we're talking about. So let's go straight to some examples. So we're going to take the definite integral of 5 from 0 to 2, or from 0 to 2 of 5 dx. So these are all the integrals we have today are all pretty easy. I didn't make them very challenging. We will learn methods of finding integrals later, but this is pretty easy. So if we have from 0 to 2 of 5 dx, let's first take the integral of this. Well, we have to kind of think backwards here. What would give us a derivative of 5? Well, wouldn't 5x give us a derivative of 5? Because remember, the x goes away when we find derivatives. So the antiderivative of 5 would be 5x. So we would say 5x, and then this symbol right here shows that we've taken the derivative already, and that we want to evaluate it from 0 to 2. So this means I've already taken the derivative, and from 0 to 2, and then we just evaluate. We plug in 2 and subtract. So we take the upper bound, plug in our value, and then we subtract the lower bound value from it. So it'd be 5x, but 5 times 2, minus 5 times 0, just like that. And I always like to put the second integral, or the second one, inside a brackets or a parenthesis, just because if there are multiple terms, you'd have to distribute this negative. That won't be the case in this case, though. So what is 5 times 2? That's 10. This is 0. So our answer here is 10. So what does this mean? It means that from 0 to 2 of the function 5, there are 10 square units under that straight line. And that kind of makes sense, right? 5 times 2 is 10. All right. Now on to this one. So same concept. So we want to take the antiderivative. We want to integrate this. So that would give us 4x. And we're evaluating from -3 to 3. And then we just plug it in. So 4 times 3 minus 4 times -3. And let's see here. That's going to give us 12 minus -12. Well, that's going to be the same thing as minus a plus. So this is going to be 24. Just like that. And that's the area under the curve from x equals -3 to x equals +3. So, and that makes sense. Look, if we had, it makes sense that it's 24, because if we had a set of axes here, and we go from -3 to 3, and we have our line at y equals 4, isn't this area right here going to be 24? 6 times 4 is 24. There we have it. Same thing here. 5 times 2, that's 10. All right, let's move on. So now we have some other kinds that we'll be seeing. So here we have the integral from 0 to pi halves of cosine x. So let's recall how the derivatives worked of sine and cosine. So remember we would start with sine x, and the derivative of that was cosine x. derivative of that was negative sine x, and derivative of that was negative cosine x, and then it just kind of restarted again. Derivative of negative cosine x is sine x, and so on. Well, if we're starting at cosine x, doesn't it make sense that the derivative, or the antiderivative of cosine is sine? And yeah, that's exactly how it works. So we can say sine of x from 0 to pi halves. And let's see here. So now let's evaluate. So we're going to have sine of pi over 2 minus sine of 0. I forgot to put my brackets that time, but that's okay. That'll be okay. Well, the sine of 1/2, or sine of pi halves, is just 1. The sine of 0 is just 0, so this is going to be 1 minus 0, which is just 1. Awesome. So that is the area under the cosine curve from x equals 0 to x equals pi halves. All right. Now this one, let's see. So this is going to be kind of an interesting one. What gives us a derivative of x? Well, we know to get an x, we need an x squared, right? We need like an x squared, but if we take the derivative of x squared, that's going to give us 2x. So how about 1/2 x squared? Let's think about this. If I take the derivative of this, 2 times 1/2 is just 1. That's just going to give me x. So from 0 to 5, that's our bounds. So let's evaluate now. So 1/2 5 squared minus 1/2 0 squared. Well, 5 squared is 25, times 1/2 is 12.5. And this is just going to zero out, so it's going to be minus 0, which is just 12.5. Awesome. Next, we have pi. So pi is just a constant, so that means the antiderivative of pi is going to be pi x. Right? If it's just a constant, just like how we dealt with 5 and 4 earlier. So here, 4 pi minus pi times 0, and this is just going to be 4 pi. Awesome. This last one, what's the derivative of e to the x? Well, it's e to the x. So what's the antiderivative of e to the x? Well, that's going to be e to the x as well. So we have e to the x from 0 to 1. Let's see, x to the first power minus e to the 0th power. And let's see. Well, e to the first power, just e. Anything to the 0th power is just 1. So this is going to be e minus 1. And there we have it. That is the antiderivative. My dog is barking. I hope this helped. Or the indefinite, or this is the definite integral. I hope that helped. Have a good day, y'all. Bye.